Hello, my name is Mohammad Hussein Taruk, and I would like to welcome you on this introductory course about electromagnetic compatibility. The reason I decided to record this small course for you is that I see a lot of videos on how to designing PCBs and how to get started using these available software tools such as KiCad, Altium, Eagle, and other tools that we have. But oftentimes I don't see anyone addressing the need of suppressing noise and avoiding interference, and in general talking about EMC topics. So in this series of videos I will talk about electromagnetic interference, electromagnetic compatibility, and how we can actually improve our design if we know a little bit about them. So during this course we'll discuss these actually 8 parts. First, introduction to electromagnetic compatibility. Then we will get to know some PCB and EDA tools, as you might already know, and then we go to grounding and other topics as you see here, such as power distribution, digital circuit radiation, RF and transient immunity, and mixed signal circuits, stack up, and PCB. And also we'll end our course with a practical example as a summary. So, what is electromagnetic compatibility and why is it important for us as PCB and system designers? So this picture is a very good picture of showing a source of radiation, a source of noise, which is having a negative impact on a victim, and it's doing it either in an inductive manner or in a conductive manner, as you see here. So you have inductive coupling and you have capacitive coupling, and also in form of radiation. So oftentimes we have this problem, and we don't want to be the source of excessive radiation, and we also don't want to be the victim of radiation from others. And that's where electromagnetic compatibility, or in short EMC, comes to play. So we know that nowadays we're using electronics and embedded systems everywhere, and this causes EMC issues. Mostly these systems affect each other adversely, and since we have nowadays integrated circuits, large scale integration, this has reduced the size of electronic circuits, and small and complicated circuitry increases the probability of interference. And in addition, we know that clock frequencies has increased dramatically over years, and above gigahertz systems are quite common today. We'll see why these high frequencies are a problem. So what is noise? Noise is any electrical signal present in a circuit other than the desired signal. Noise sources can be grouped into the following categories. We either have intrinsic noise sources, which come from the device and the circuits themselves. We have man-made sources, noise sources, such as ESD, and we also have noise caused by natural disturbances. For example, lightning or sunspots. And interference is the undesirable effect of noise. So we should not mix these two definitions. Noise is any unwanted electrical signal, and interference is when this unwanted electrical signal is causing a problem, an undesirable effect in our circuit. And it's also good to know that noise cannot be eliminated, but interference can. So it means that we cannot remove noise, but we can remove its impact, which is interference. So for noise to exist, we need to have a noise path. So we have a noise source, a coupling channel, and also a receptor. So these are the 3 elements required for noise to exist. And also there are the frequency, the amplitude, and the time at which the noise is happening. So at which frequency this problem is happening? Does it occur at 50 Hertz, or does it occur at 10 kilohertz or 1 gigahertz? So this is the frequency. And what is the amplitude of this noise, which is, for example, I see on the output of my signal, or on my output channel? Is it 1 millivolt? Is it 1 microvolt? Is it 1 volt? How much is it? And also the time. When does this appear? Does it appear when I turn on the system, or does it appear 10 minutes after the system is running? Or does this noise problem occurs when I turn on another device connected to the same network? So this is very important. You need to know the FAT, which is the short form of the first letters of these words, the FAT characteristics of your noise. So you need to know the source of noise, the victim of noise, the coupling channel, and also the FAT. So now we discuss a little about the noise coupling methods. The first is the conductive coupled noise. So as an example, we have radiation from a three-phase motor leads. As an example, you have a three-phase inverter and you have a three-phase motor, and there's a low-level circuit, analog circuit, close to your, for example, inverter, and the radiation from the cables, which are called in this case conducted emissions, are causing measurement errors in your card. So this is called conductive coupled noise. Then you have common impedance coupling. You have two circuits that have the same ground, and the ground noise created by switching, for example, by switching supply, or a circuit which has high turn on and turn off currents like motors and relays, disturbs the precisions of your amplifiers. So this is very common in PCB design, that you have precision measurements and also you have switching mode power supplies, and they have the same ground. So the return current, as you see here, of the switching power supply can create a ground noise because of the ground impedance that can disturb the ground of your precision circuits. And also you have the electric and magnetic field coupling. You know, we have a lot of RF radiation and electromagnetic waves around us from, for example, the intentional radiators and unintentional radiators. So you have the RF radiation from nearby telecommunication antennas, or from magnetic fields and electric fields from power mains running, I don't know, maybe in a close by area. And they impact your precision amplifier circuits here as an example. So now we know these three coupling methods. So if you want to define EMC, or electromagnetic compatibility, it's the ability of a system to function properly in its intended electromagnetic environment and not being a source of pollution to that electromagnetic environment. So EMC has two aspects. One aspect is emission, how the system emits electromagnetic waves in its working environment, and susceptibility, how the system is affected by its operating environment. And experience has shown that when EMC is considered from the beginning, 90% or more of the potential problems are eliminated before initial testing. So it's something that we need to think of from the design. When we're doing the design, when we're doing our PCB design, we should think of, for example, how should my grounding system be? So when the system is manufactured and ready to be tested, we don't have problems, or at least we have minimal problems. So here's the graph that you see that I took from a famous book in the field of EMC, which is called Electromagnetic Compatibility Engineering, from Otto Henry, if I'm not saying his name wrongly actually. And it shows that if you consider different phases of a product being developed from design to production, if you can identify and solve the problems related to EMC during the design and testing, then the costs will go down. But on the other hand, if you don't think of it, and if you take a disaster approach, as we say in EMC, like you disregard the EMC guidelines and you just do the design and go to the end, then once you're in production phase and then you want to solve these problems, it will be very expensive. You have to do design revisions, you have to order new PCBs, you have to do new assembly, again, type testing, or to say standard testing. You need to send your equipment to an EMC lab, and that costs you a lot of time and also a lot of money. So this is important to know, that EMC, when you disregard it from the beginning, can be very costly. So let's get to the PCB and EDA tools. So we know what a PCB is. PCB is what mechanically supports and electrically connects electronic components and electrical components. We know that PCB uses conductive tracks, pads, and other features like on one or more layers, and usually the layers are in like the multiples of 2, so that we have reliable circuits. So far, the printed circuit board technology is the most reliable technology that we have to implement electronic circuits. You see here 2 examples. For example, the Arduino Mega 26050 and 26550, sorry, and also ESP32. These are the examples of printed circuit boards that you probably know already. So in case of PCB, we always have a core made of some dielectric material, and then you have, this is the basic 2-layer stack up PCB structure. You have the bottom layer and you have the top layer, and you have higher layers. And for higher layer PCBs, then you have a core and you have middle layers or internal layers, and we'll get into that later in more details. But here it's good to know that then we have, they call these additional dielectric layers as prepregs. So we have the core and the prepregs that structure your PCB. So this is also a definition of, or actually terminology used in PCB, like trace, power and ground plane. You know, the trace is the copper connection of components like wire in electrical systems. Power and ground plane are copper or grid areas in PCB that are used to distribute power and or ground conductor in the circuit to make them as ideal as possible. Placement is how the components are placed on the board. This is a very important step. We have pads, the place where component pins are soldered to the board is called pad. Routing is the process of connecting component pins together to form the circuits. Footprint is, or a land pattern, is the arrangement of pads of a component. And you also have microstrip, a trace above a ground or power plane. Also, we have a trace between 2 ground. Strip line, if you have a trace between 2 ground or power planes, then this is called a strip line. And we have via holes in the PCB that connects different layers. If you want to move, for example, from layer 1 to layer 4, then this is done through vias. And stack up is the PCB layer spacing, material and characteristics, how you structure, how you distance them, and what's the thickness of every layer. So this is an example of a HDI or high density interconnect board, which you nowadays see in different equipment like smartphones, or I don't know, computers and things like this. And you see all those terminologies that I explained. You see the footprints, is where these connectors are connected. It's the footprint of a most probably a DDR3 RAM connector. These SODIMM modules will plug in. You here have the footprint of an IC, different ICs, BGAs, bulk grid array ICs. You have here small outline packages, and also the footprints of different ICs, transistors, capacitors. Here C shows capacitor, R for resistor, and so on. The difference between normal PCBs and high density interconnect is, one difference is that they have micro vias and buried vias, but you don't have them in normal PCBs. So the vias go all the way through the board. So if you come back here, this is a through hole via. It goes all the way through your board. So this is a normal PCB. But if it just goes from layer 1 to layer 2, for example, then it's a blind via. Or if it just goes from layer 2 to layer 3, then it's kind of a buried via. And this is the difference, because then you can make your routing and your traces more dense and dense. So if you want to use a design tool, always consider these things. First, think if your tool is paid or free. Sometimes it's not a problem for you, sometimes it is. For makers, for hobbyists, it's a big problem if they have to pay a large amount of money for a software like Altium. Also think of the availability for Windows, Linux, and Mac. So think of your OS and what software is there for your OS. Nowadays we also have these online tools like Upverter, like others. So you don't need any offline software, so you can also use them. Think of also having unlimited number of layers and unlimited file size. So sometimes softwares like KiCad, they give you this open source ability to have unlimited layers, unlimited file size, but others will limit you for free licenses. You also need good dedicated schematic and PCB layout tools because they are the most important thing that you get. These tools will save you a lot of time and also help you to create advanced circuits. So you definitely should think of it. Does it work if I use KiCad, for example, or Altium now that I'm using it for a company use, or maybe Eagle? So you should think of it. And also think of standard file generation like Gerber files, bill of materials, pick and place files, and other standard files that you might need for assembly, for manufacturing, and things like this. Now let's get to grounding. So it's a beautiful picture. Here we have, and it shows different grounding methods, signal grounding methods. We will explain later. So, despite the fact that ground is the most important conductor in a circuit, it's the one that gets the least attention. And grounding is the primary way of minimizing unwanted noise and producing a safe system. And you should always consider that a good ground system is always required. So it's a must. It might seem strange to spend expensive engineering time on this, but this worth it. You need a correct and properly designed ground system. It saves you both time and money when you're testing the equipment, the correct grounding system. And it's also good to know that well-designed ground system often provides protection against unwanted interference and emission without any additional cost. So if you have a good grounding system, it's probably that you don't need to add, for example, filters in order to reduce interference. So this is also important. Grounding is important but always misunderstood when it comes to noise and interference. Different people have different understanding of ground. Some people think of it as the earth connection, some people think of it as the safety green wire, some people think of it as ground and plane, and some people think of it as just a narrow piece of PCB trace, which is used at low frequency analog signals. So different people have different understanding of ground, but we want to categorize the ground in two broad categories, either safety grounds or signal grounds. So safety ground is mostly and often do not carry any current unless there's a fault. So for example, here in this picture you see a simple electrical system which is used at homes. So you have 120 volts at hot line and also the neutral line, but also you have this green line which is connected to your metallic enclosure, and it is also linked to the earth system. So if there is by accident a connection from the hot line or any other part of this load connects to the enclosure and connects to 120 volts, then it will cause the fuse to blow or the circuit breaker to blow, and it will protect the circuit. And as you see, the current through this green safety ground just happens during a fault and not normal operation. During the normal operation, the current goes through this loop. You also have something called as chassis ground, which is the ground connected to the chassis or the enclosure of the equipment. If you have metallic enclosures, or for example in the car or in airplanes, that metallic body that they have is considered as chassis. So chassis are usually connected to earth or some conducting body that serves in place of earth. The objective of grounding should always be to make it first safe and work. So should always first consider safety. So oftentimes people know ground as an equipotential point or plane, which serves as a reference for all the circuitry in your PCB or in your system. And this is the voltage definition of ground. But this definition isn't appropriate for a practical ground system, because in reality ground systems are not equipotential first, because we have impedance, and this impedance is different in different parts of your ground, and this definition does not emphasize the importance of the path taken by the ground return current. So it thinks that ground is something magical that all the currents go through, as you see in the schematic, without thinking where it actually and how it actually returns to the source. So a better definition would be ground is a low impedance path for current to return to the source. So low impedance paths for current to return to the source. So this is the ground, or this is called the current definition of ground, and it's considering both the impedance and the return current or return path. So when we have this definition of ground, now we know that we can evaluate the emission and susceptibility, because we can somehow evaluate the impedance of our ground. We know that impedance has a resistive part and also imaginary part. So we have an impedance in our ground, and we have a ground voltage, which is referred to as ground noise. So ideally, and we are looking for either not to interrupt the return current path, and we want to return the current through the smallest loop possible. That's why you always hear people suggesting you to make all the traces in your circuit as short as possible, because then these shorter traces will make shorter paths and shorter loops. And being aware of the impedance coupling, common impedance coupling that we also saw an example of when we have two circuits that share the common ground. So VG, or ground noise, we want to decrease it, and in order to decrease this voltage, we either have to minimize the ground inductance, or actually impedance, for high frequency and digital circuits using a ground grid or a ground plane, as we'll see, and we also want to decrease the IG, or the current which is going through our PCB, by forcing it to take a different path. So we use not the same ground, maybe it's different plane or different trace, so that it has a different path. And we usually use it for just low frequency, for example, analog circuits. So now we have in signal grounds different types of grounding methods. We have single point groundings, and in single point grounding we have serial single point connection and parallel single point connection. So in serial single point connection, as you see, they are connected in this manner. So if I go back a bit and come to the first, so here you see this serial ground connection. So the problem here is that the current from the third load will also appear on the ground conductor of the second and the first one. So the effect of the inductance here, or the impedance here, will be significant. On the other hand, if we use this method, then the current of the third circuit is not flowing from the ground of the other one, so it's directly going to a ground point, let's say, in your circuit. So then there won't be excessive voltage drop. Then you won't have different voltages. Here the voltage at point C is more than at point B and point A. So you have different voltages, different ground potentials, and you don't want to avoid this. So for low frequency circuits from DC to maybe 220 kilohertz, you use this single point grounds, and ideally try to use this one, not the first one. But at high frequencies, and you go above 1 megahertz maybe, or 100 kilohertz, because of this stray capacitance here, you will actually have a multi-point ground. You see it here. So this stray capacitance will shorten your, or will short your trace, and you will have anyway a multi-point ground. So for high frequency digital circuits that I'm sure you're using more often, like microcontrollers or FPGAs, you should always try to have a multi-point connection. And multi-point connection is created when you have a ground plane and you connect your circuit ground directly to that ground plane. This creates the smallest possible loop, and also it creates the smallest amount of inductance, as we'll see. And one important thing about the chase's ground is we most of the times, or sometimes, we have a metallic enclosure, and this is important from noise point of view, and later also from transient and EST point of view, that you connect your enclosure, which is metallic, to your ground, to the ground of your circuit ground, exactly at the point where the conductors leave or enter your PCB. So this tells you that this is not a good idea to have a PCB that the conductors or the cables are entering and exiting from different sides of the PCB. It's always best to keep them on one side, and from that side is the best where you connect your circuit ground to your enclosure. Also, in case of electrostatic discharge, it will protect your circuit. So they're connected at one or more point, in order to decrease the inductance, but here at the entry of cables. Let's say for a case that you have cables. So here's also an example of a plane, ground plane, and a chassis plane. So here you have, this is actually something that I would say is wrong, because if you have a ground plane here, if the cables are entering from here, then you can easily connect it to your ground, and then it will be the same thing that we have here. I think this is a wrong thing. I saw this picture in the internet, and I think you can also see the link, and it shows a wrong kind of chasis. It doesn't matter if this chasis is open or it's closed. When it's connected to the ground and it's basically at the same potential as the ground, then there won't be any radiation, because then radiation occurs when this chasis is not connected to ground and it's at a different potential as your noise ground. Then it can act as an antenna. So let's not get into that. Let's go to digital grounding, but in order to discuss that, I will do it in the next video.